All right, let's look at this interesting phenomenon called beats. When we combine two sounds with similar frequencies, we hear fluctuations in its amplitude called beats. All right, let's demonstrate. All right, so here is an online tone generator, and I'm going to play 440 hertz, which sounds like this. Then I'm going to play 441 hertz at the same time. Right? So we can hear these fluctuations, 1, 1, 1. So we can hear 1 beat per second when the difference between frequencies is 1. When we do 442 hertz, we're going to hear 1, 2, 1, 2, 1, 2, 2 beats per second. And we can do 3 beats per second and 4 beats per second, 5 beats per second, and so on. All right, I'm going to turn these off before we go crazy. All right, so it looks like the number of beats per second is determined by the positive difference between two frequencies, F1 and F2. All right, so let's try to understand this formula mathematically. All right, so I'm going to use two sine curves to represent those two sounds, right? A sine of omega 1t and a sine of omega 2t. All right, so I'm going to use this trig identity where a plus b corresponds to omega 1t and a minus b corresponds to omega 2t. And we can combine those two sine curves as this. All right, so we're going to have 2, and I put the cosine of b first here for our purposes, and then sine of a second. All right, you notice that since f1 and f2 are close together, similar, and omega 1 and omega 2 are similar, so we're going to have a small frequency for cosine, and since it's a subtraction, and since it's an addition, it's going to have a high frequency for the sine. Right, so what happens is this cosine curve is going to act like an amplitude function, right? Let's look at the picture. Right, so I'm going to open up GeoGebra here. So this is the graph of sine of omega 1t plus sine of omega 2t. And I'm using 51 hertz and 50 hertz. And maybe I'm going to open up yeah, this is a 1 second window. So you can see that you have one bump, one beats. And if you change the frequency to say 52, right, you see 1.5 here and a half here. So two beats. And then 53, you have 3 beats, 4 beats, and then 5 beats per second, right? And you can see that here, amplitude curve is going to determine the behavior of the beats, right? So let's try to find the frequency of the amplitude function, right? So I'm going to write down the amplitude function, which looks like this, which is just first part of this function here, right? So amplitude function, and its frequency is going to be simply circular frequency divided by 2 pi, right? So I'm going to distribute the division by 2 pi to omega 1 and omega 2, but omega 1 divided by 2 pi is same thing as f1, and omega 2 divided by 2 pi is same thing as f2, and then divide by 2, right? If you look at the picture, right, maybe I'm going to go down to here, right? So if you look at the one cycle of the amplitude function, one cycle is from here to there. So you can see that the one cycle of the amplitude function, it actually contains 2 beats, right? So the number of beats is going to be twice as many as the number of cycles of the amplitude function. So we need to multiply the frequency by 2. So beat frequency is going to be 2 times the frequency of the amplitude function. So the 2 cancels out, so you end up with f1 minus f2. Right, that's why we have this formula, f1 minus f2. And the absolute value sign is there just in case it's f1 is smaller than f2, right? But with the absolute value sign, we can make sure that we have the positive difference, right? That's it. I hope that this was clear.